Hello. Today we are going to look at limit theorems. And we mentioned last time, or time before, that the definition is difficult to work with in terms of proving things. And you saw that when we did some epsilon delta proofs. Definitions that generally aren't made to prove with. They are made to be exact and precise and define what we want to define in a very special way. Instead, what we do is we create theorems, lemmas, things that we can use to prove what we want to prove. And those come between the problem and the king, so to speak, the definition, and they satisfy the king. Now, all of those theorems technically have to be proven by the definition, or something that we use the definition to prove. So it's ultimately, the king has to be satisfied, but generally the theorems and lemmas are easier to work with. And so we're going to look at a couple of them. We're going to try and prove a couple of them. And there's a lot of them. We're going to assume the rest, but technically all of them would have to be proven basically the same way. So the first one we want to look at is uniqueness of a limit. In other words, prove if the limit as x approaches a of f of x exists, then it is unique. Okay, and so again, we're going to prove this using the definition, and we're going to prove it actually by what's called a proof by contradiction. We're going to assume that the result is not true and then get a contradiction. Therefore, the original assumption had to be false, hence the theorem is true. It's kind of like saying, if I had done such and such, then this would have happened. But since this didn't happen, I didn't do such and such. Fill in the blanks there, whatever you want to put in. So that is the process of a proof by contradiction. So let's suppose the limit as x approaches a of f of x equals L, and the limit as x approaches a of f of x equals M, where L is not equal to M. Okay, so we have two different limit values. So let's let epsilon be the absolute value of L minus M. And since these we're assuming are not equal to each other, note here, epsilon is greater than 0, which is good, and we need that. Now, the limit as x approaches a of f of x equals L means there exists delta 1 greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta 1, then absolute value of f of x minus L is less than epsilon over 2. And why am I picking epsilon over 2? Because it is a positive real number, and ultimately it will be what we need to make it work. So you'll see why when we get to it, but it's one of those things that we can pick any positive real number by the definition, so I'm going to pick epsilon over 2. And then similarly, since the limit is also M, there exists delta 2 greater than 0, such that if 0 is less than the absolute value of x minus a less than delta 2, then the absolute value of f of x minus m is less than epsilon over 2. So both of these things are true. Hopefully it's not too low on the board to see. Now, let's let delta equal the min of delta 1 and delta 2. So by doing that, now both of these things will be true. We will have that both f of x, the absolute value of f of x minus L is less than epsilon over 2, and the absolute value of f of x minus m is also less than epsilon over 2. So then, if 0 is less than the absolute value of x minus a is less than delta, then epsilon, which is, again, we said the absolute value of L minus m, is equal to, do some algebra here, L minus f of x plus f of x minus m, just adding and subtracting the same amount, which is less than or equal to the absolute value of L minus f of x plus the absolute value of f of x minus m. This is our friend, the triangle inequality. Remember I said that that would become important. We would use it. Here we are. Which is, I can flip this around, multiply by negative 1 on the inside, the absolute value of which is 1, so it doesn't change anything. F of x minus L plus the absolute value f of x minus m, which is less than epsilon over 2. That's the first part right here. And plus epsilon over 2. That's the second one right here. And now you hopefully can see why I chose epsilon over 2, because then when we add those, we get epsilon. And putting this string together, we get epsilon is equal, equal, less than or equal to, equal, less than, equal, and we take the most restrictive of that, which is less than. Epsilon is less than epsilon, which is impossible. And usually in mathematics, or oftentimes in mathematics, we write something that's impossible. This is the notation that we use. Means that it can't happen. Therefore, the limit is unique if it exists. Okay? We assumed it wasn't. We got a contradiction. Therefore, that assumption had to be wrong. Hence, it must be unique. Okay? Let's look at another proof of a limit theorem. These are sometimes called limit laws. You'll find a list of them in your book. But next one I want to prove is the sum theorem, which says if the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to m, then the limit as x approaches a of f of x plus g of x should be L plus m. And it is. Okay? And this we are going to prove straightforward, called a direct proof. So, let epsilon be greater than 0. Just a generic epsilon greater than 0. Then if, well, let me back up here. Since the limit as x approaches a of f of x is equal to L, there exists, same basic idea before, delta 1 greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta 1, then the absolute value of f of x minus L is less than, again, I'm going to choose epsilon over 2 for basically the same reason as I did previously. And again, the limit as x approaches a of g of x equals m implies there exists delta 2 greater than 0 such that if 0 is less than the absolute value of x minus a is less than delta 2, then the absolute value of g of x minus L is less than epsilon over 2. So same basic idea, except I have two different functions, f of x and g of x. We're going to start this last, putting these together basically the same way as I did before. Let delta equal the min of delta 1 and delta 2, which means both of these are going to be true if 0 is less than the absolute value of x minus a is less than delta. Both of these individual results will end up being true, and we will use them just like before. Then, the absolute value of f of x plus g of x minus L plus m. I need to end up showing that this is less than epsilon, because then that will show that this is the limit, is equal to the absolute value of f of x minus L plus g of x minus m, distributing and rearranging. Again, I'll use the triangle inequality. Absolute value of f of x minus L plus absolute value of g of x minus m. We add less than or equal to that by the triangle inequality, which is less than epsilon over 2 plus epsilon over 2, again, using those two pieces, which obviously equals epsilon. And so therefore, putting it together, we get the limit as x approaches a of f of x plus g of x must equal L plus m, which is exactly what we wanted to prove. Okay? As I mentioned, technically all of the limit laws or limit theorems would have to be proven in this manner. It isn't that useful to keep doing this, but if you're interested in that kind of thing like I am, then you find it kind of interesting. We will assume all the rest of the limit theorems that are basically in your book. And the limit theorems basically say as long as nothing bad happens, then the value of the limit is going to be what we expect it to be. We can the limit value is going to be the same as the functional value in a lot of cases, as long as something unusual doesn't happen. That's basically what the limit laws say and prove. We will show later that the limit as x approaches a of sine of x is sine of a, that sine is a very nice function in that matter, similar for cosine. And therefore your trig functions are all nice in that way as long as things are defined. Again, basically, as long as something bad doesn't happen, and I really shouldn't call it bad, as long as something unusual doesn't happen, the limit value is the functional value. even though technically you cannot input, when you're finding a limit, you don't technically input the value to get the limit. We'll see what it approaches, but the point is that as long as something unusual doesn't happen, what it approaches is going to be the same thing as what it actually is. Again, make sure you keep those concepts, understand they're different concepts. The value that the function approaches does not have to be the value that the function is at some value x equal a. F of a does not have to be the limit as x approaches a of f of x. Okay. One other theorem that's kind of useful at times, and that is called the squeeze theorem. And I'm not going to prove this. Just give it. Squeeze theorem says if f of x is less than or equal to g of x is less than or equal to h of x for all x in an open interval, around x equal a, except possibly x equal a itself. And later I'm going to call it, well, I'll probably from now on call this a deleted open neighbor interval. So I don't have to write all that stuff out. If we have this is true and the limit as x approaches a of f of x is L, and the limit as x approaches a of h of x is equal to L, then the limit as x approaches a of g of x has to be L. And the idea is that I have a function, let's call this f, and I have a function g in the middle, and which I'll do last, and I have a function h on top, and we have, and this is my value x equal a. And notice that there is an open interval here where in that interval we have f on the bottom, g in the middle, h on top. And the point is that if the limit of f is L and the limit of h is L, then g being in the middle gets squeezed. It has to have a limit value of L. It's kind of basic when you think about it. We're not going to prove it. But anyway, we will end up using this on occasion. It kind of pops up in some unusual times. So I will remind you of it when we use it.